Here in this video, we're going to look at some integration rules, and I'm going to compare that to our differentiation formulas that we've learned before and how they relate to your integration formulas. So if we start off with d dx of c, where c is just a constant, we know that's going to be 0. For example, if I was to say we want to take d dx of 4, so the derivative here of 4 would simply be 0 because we know the derivative of a constant is 0. Well, the integration formula says, well, if we integrate 0, so simply if we integrate 0 dx, then you're going to end up with some constant. All right, so over here on the left, if we take the derivative of k times x, and k is representing your constant, so for example, if we have d dx of, let's say, 2x, then we know the derivative would simply be 2. Well, if we look at the integral of k dx, for example, if we have the integral of 2 dx, then this is we're integrating a constant, so we know that all we're going to have to do to integrate a constant is we know there used to be a variable there, because over here when we took the derivative of 2x it was 2, so for the integral we would just simply multiply then by a variable x, so we have 2x, and we have to remember there could be another constant here, so that would be 2x plus c. And keep in mind, you can always check your answer. If we go backwards now, if we take the derivative of 2x plus c, the derivative of 2x is 2, and of course the derivative of c is 0, so the derivative of 2x plus c is simply 2. So if you want to ever check your integration, all you need to do is take the derivative of your answer, and that should be equal to the integrand. All right, over here on the left we have the derivative of k times f of x. So basically what that says is if you have k as a constant multiple here, constant multiplier, so if we had, for example, the derivative of 2 times x cubed plus 3, then we know that there's two ways we could handle this. We could actually distribute the 2 to get 2x cubed plus 6 and then take the derivative, or what this formula tells us is we can leave the 2 as a multiplier because it's just a constant, and we take the derivative of x cubed, we know that's going to simply be 3x squared, and the derivative of 3 is 0. So we get 2 times 3x squared, where k over here, our constant, is 2, and f prime of x would be our 3x squared. So we would certainly then multiply that, and the answer would be 6x squared. Now for the integral, we have k times f of x, and here with the integral what we're saying is if you have this constant k, we can actually pull that k out in front of the integral and simply find the integral of the function and then multiply by the constant. So if we were looking at, say, the integral of 2x squared dx, then what that means is we could take this 2, which is a constant multiplier, pull that out front of the integral sign, and all we have is x squared dx. And then from here we could actually then integrate that further, and if we did that, you would increase your exponent by 1. But here I just want you to see the formula, what this means. If you have the integral of a constant times the function dx, then that constant multiplier can be pulled out in front of your integral. All right, the next derivative formula on the left here simply says the integral of the derivative rather of f of x plus or minus g of x, says we can simply just take the derivative of function f and then add or subtract it to the derivative of function g. So all we're doing is adding or subtracting the two derivatives together. And over here on the right for the integral, we can do the same thing. If we have the integral of some function f plus or minus another function g, we can actually think of splitting that up into separate integrals and then integrating each one of those separately. Okay? Now, here's the important part. If we look at our derivative over here on the left, we know the derivative of x to a power, x to the n. We simply multiply the exponent out front, so we get n times x, and then we subtract 1 from the exponent. So an example there would be if we had d dx of x to the fourth, then we know the rule is we're going to pull the 4 and multiply out front, so we get 4x, and then decrease the exponent, so we have 4x cubed. So over here on the right, when we're integrating, we're going to do just the opposite. So if you notice here the formula now, we have x to the n dx. So here, instead of subtracting 1, we're going to have to do the opposite. We're going to have to add 1 up here to the exponent. So that's where we get x to the n plus 1. And instead of multiplying, we're going to divide by n plus 1. And this here is called the power rule that we're talking about. And this is what you really have to understand. This is the majority of some of your basic integration here, is simply increasing the exponent by 1 and then dividing by the exponent. All right, and quickly here, I'm not going to look at each one of these, but you'll notice down here below all the derivatives of your trig functions. And I said before, basically you just memorize these. If the derivative of sine x equals cosine, then on the right, clearly the integral of cosine is equal to sine of x and then plus c for any added on constant. And if the derivative of cosine equals negative sine, then the integral of sine must be equal to negative cosine. So be careful here with your positive and negative signs between taking the derivative and integrating. And of course the derivative of tangent is secant squared, so that means that the integral of secant squared would simply be tangent. And then if the derivative of secant is secant tangent, then the integral of secant tangent would be secant x. And if the derivative of cotangent is a negative cosecant squared, then cosecant squared, the integral of cosecant squared, is negative cotangent. And the derivative of cosecant is a negative cosecant cotangent. So the integral cosecant cotangent is a negative cosecant. So I know I went through those rather quickly, but basically you just need to spend some time, look through these integrals and realize they're there, and you have your formula sheet to look at the integration rules for these particular trig functions. And I would suggest memorizing the integral of cosine, the integral of sine, and then gradually you could pick up some of these others, but you definitely want to memorize the integral of the cosine and the integral of your sine function. So now let's look at some examples of integration. If we have the integral of 6x cubed plus 4x squared minus 3x plus 9 dx, then we could think of this problem as setting up each one as a separate integral, such as the integral of 6x cubed dx plus the integral of 4x squared dx minus the integral 3x dx plus the integral of 9 dx. Now that's what we can do up here using this formula above right here, where it says we have the integral of f of x plus or minus g of x. You can split it into separate integrals, and that's what we have here. Now most likely you're not going to do this. We can mentally do this without having to write down all 4 of these separate integrals. For example, over here we could look at 6x cubed, and the rule for this is to take your exponent and increase it, so 3 plus 1 is 4, and then you're going to simply divide by 4. So there's the integral of 6x cubed. And then we have 4x squared, so that becomes 4x cubed divided by 3 minus 3x squared divided by 2 And then 9, we simply multiply the x, so that becomes 9x. And you don't want to forget there's always a plus c for any constant that's added on. So there is your integral. And at this point, all we have to do is simplify. So from here, we could simplify this. 6 over 4, we could write this as 3x to the 4th over 2 plus 4x cubed over 3 minus 3x squared over 2 plus 9x plus c. Now I do want to mention an alternate way of writing this. Hopefully you know this is the same. We could always write 3/2 times x to the 4th plus 4/3 x cubed minus 3/2 x squared plus 9x plus c. So either one of these would be correct. All right, the next example here we have the integral of x times 7x squared plus 4 dx. And if you notice here, we have multiplication. Now, when we were taking the derivative, we had a product rule. Well, if you look above at our examples that we don't have a product rule for integration. So the only way that we can handle this problem is to first, we need to rewrite this problem. And essentially that means we need to distribute the x. So if we rewrite it, then we can actually integrate this. So if we rewrite the problem by distributing, we would end up with 7x cubed plus 4x. And now we can integrate because we just have our separate terms. So we would have 7x, increase it to the 4th, or divide by the exponent, so that's divided by 4. And then we have 4x, increase the exponent, so that becomes squared, divided by 2. And from here, all we have left is to simplify, so we could write this as 7/4 x to the 4th plus 2x squared plus c. All right, the next example, notice we have 1 over 4x squared. Here we're dividing with a fraction. And before with the derivative, we had a quotient rule. Well, once again, for integration, there is no quotient rule. So therefore, once again, we need to rewrite this. And if we rewrite the integral, we could think of this as, instead of 1 over 4x squared, if we move this x squared to the top, notice I'm going to leave the 4 on the bottom. And if I move the x to the top, that means our exponent would become a -2. So this is kind of the reverse of what we normally do. Normally we have a -2 and we want to make that exponent positive and we move it to the bottom, but here we're going to move it to the top. So now we can certainly just integrate from here. Now there's another option here. You don't have to do this, but notice we're dividing by 4. You could think of this as the integral of 1/4 x to the -2 dx. And you could even go a step further and say, well, what about this 1/4? The 1/4 is just a constant multiplier. So as we did up here above, in this step here, notice we have k f of x. You could pull this k out front. So we're doing the same thing here like we did the 2x squared. We pulled the 2 out front. So down here we're going to do the same thing with the 1/4, and we could write this as 1/4 the integral of x to the -2 dx. So now this is in a form that we can integrate, and if we do that, we just simply bring down the 1/4 and we integrate x to the -2, so we increase the exponent. Now be careful because we have a negative exponent. You may want to say this to yourself out loud, because if you increase the exponent, now it's going to become, you're adding 1, so that's x to the -1 divided by -1. Don't make the mistake and say it's x to the -3, because that means you're subtracting. So we have to add 1, so that's x to the -1 divided by negative 1 plus our constant. So then at this point, there's the integral. We could simplify this by writing this as 1/4 times, move the x to the negative 1 to the bottom, that just comes x to the positive 1 and you could leave it this way, and because we have the negative, I would probably write this as then negative 1 over 4x plus c. Now, real quickly here, I want to show you that if we did get to this point as an alternate way here, we could leave this as the integral of 1/4 x to the negative 2 dx. If we do that, we could simply integrate. We would just still have the 1/4, and we would take x, raise that to the negative 1 divided by negative 1. And once again here, whether you pull the 1/4 out or not, you're still going to end up with the exact same answer. You're still going to have that negative 1 over 4x plus c. So it's kind of up to you. Some problems it's just as well to leave this constant inside. For other problems, it's to your advantage to pull it out front in front of the integral. All right, now this example looks very similar to the one above, but we need to be careful. Notice now we have 1 over 4x, and the whole 4x is being squared. What I would suggest here is, again, we need to rewrite this because we do not have a quotient rule. And in the process of rewriting, I would take and actually go ahead and square the 4x so that you would have 1 over 16x squared. I would recommend doing that before you move your variable to the top. And that's because now we could rewrite this as 1 over the 16 stays, because we're not concerned about moving the 16, we only want to move the variable, so that would then move the x to the top, and we would have x to the negative 2. And once again, at this point, we could pull the 1/16 out front, and we're left with x to the negative 2 dx. So if we integrate, make sure you bring down that constant multiplier, otherwise you will forget it. And now if we integrate, you have x, again, x to the negative 2. You're adding 1, so that becomes a negative 1 divided by negative 1 plus our constant. So once again, if we want to make your exponent positive, we're going to move that to the bottom. So we would have 1 over 16x, and of course the negative, you could leave the negative at the bottom. I always tend to write my negatives in the numerator, so I'm going to move it to the top. So we have a negative 1 over 16x plus c for your answer.